me start the recording. So we're going to finish the relational data model today, and next week we're going to switch to the entity relationship type model. So for that model, I'm going to probably quickly give you a review, and we may have 1 or 2 in-class exercise. Then we are done with the data model part. So this is what we end with the last class. So in the last class, we mainly discussed the normal forms, the first normal form, second normal form, and the third normal form, right? And also we kind of discussed different functional dependencies. So like full versus partial functional dependencies in terms of a key. And then we also discussed the transitive functional dependencies in terms of a key of a relation schema. So you just need to understand that whenever we need to evaluate the goodness of a relation schema, we have to go with the first normal form first. And the first normal form only considers the attribute's property. So as long as each attribute in the schema is atomic, then we consider that relation schema is in first normal form, or 1NF. Then regarding to the 2NF and the 3NF, we have to consider the key information of that schema along with all functional dependencies that defined on that schema. So then we can further partition the functional dependencies into 3 categories, like a full functional dependency, partial functional dependencies, and transitive functional dependencies. So if a schema is in second normal form, it must be in the first normal form first. And then it also needs to require that no non-prime attribute, is partially dependent on the key, or is dependent on the partial key. Maybe that's much easier to understand. So no non-prime attribute is dependent on the partial key. So that's basically the requirement. So in other words, we require that every non-prime attribute must dependent on the whole key. Okay, so that's requirement. So if a relation schema satisfies the second normal form, then we're going to go to the next normal form, the 3NF, or third normal form. So for the third normal form, we require that every non-prime attribute must be fully and directly dependent on the key, on one of key. But if we found there's some non-prime attributes, they are only dependent on another set of non-prime attributes, that indicate those type of functional dependencies is transitive functional dependency. So in the third normal form, no transitive functional dependency is allowed. In second normal form, no partial functional dependency is allowed. I think in the last class, we end up with kind of discussing this example. So this example is very special in the sense that it has 2 keys. Okay, so the property ID is 1 key. The second key will contain both county name and the lots number. So that's the second key. Okay, so then the property ID is underlined. That means that is the primary key. So then the county name and lots together is called secondary key. But both other keys means that they satisfy the uniqueness constraint. So means that for every record in this table, each record will have a unique property ID. And also each record will have a unique combined values of county name and lots number. Then we also have 4 functional dependencies defined on this schema. So we need to evaluate each functional dependency to categorize them either full, partial, or transitive. So now we have two full functional dependencies. So full functional dependencies are good ones. Then the partial or transitive functional dependencies, they are not good ones. So that's usually a bad sign for the design of this schema. So because both partial and transitive functional dependencies are the root cause of the redundant data that in our table. Okay, so here in this example we have one partial, one transitive. That means that this this schema is not in third normal form. It's actually even not in the second because there is a partial. So second normal form does not allow partial functional dependency. Third normal form does not allow transitive, does not allow partial. Okay, so that's since we have partial, that means this relation schema can be only in first normal form if we assume that every single attribute in this schema is atomic. Okay, so then since it's not in third normal form, then we have to normalize it, this schema, so that we can get or we can derive a set of smaller relation schemas all in 3NF. So we actually need to follow the normalization process. So this is a very good process. So it contains two steps. So step one, we're going to create a relation schema for each partial and also for each transitive functional dependency. Okay, so we're going to pick one. We create a schema for each one at a time. So in this case, since we have one partial, one transitive, so that's why we're going to create two relation schemas. So the first one is actually about that partial functional dependency. Content name determines text rate. So this text is the first one, first schema we got. The second one corresponding to that transitive functional dependency. So we have error determines price, so we have error price. Okay. Then the last one. So the step one, once we create these two schemas, we are done because we finish handling every single transitive and partial functional dependency. Then the next one, we're going to we still need to create a relation schema that contains the primary key of the original schema, that will be property ID, and any attributes that fully dependent on it. So finally, we have this one. Okay, so I think in the class, I cannot tell how to identify what should be included in the last relation schema. I think one thing that we can do is that for each functional dependency, partial and transitive, when we create a relation schema, then we're going to cross out the attributes in the original schema. Those attributes should be only on the right-hand side, the dependent. Okay, so I think in this case we can cross out. For example, I did that. So we first cross out the price. Then the second one for the transitive, for the partial, we cross out tax rate. So then remaining attributes should be included in the final step 2. Okay. So now I think. So now we have to. I think there's one more step we need to do it. We have to identify the foreign keys. Okay. Okay, so let me copy these 3 together and come here. Okay, so I just want those schemas. I don't want anything else. Okay, then now we have to specify the foreign key. Since we have 2 relation schemas, in general, we should have 2 pairs of the foreign key and the reference key. So 3 minus 1 equals 2. So we need 2 pairs. So that's the minimum amount of the foreign key and the reference key, so that we can connect all 3 tables together. Okay, so I think the first remember that foreign key always reference to the key, okay? So we just see, okay, I think we can examine each primary key, the primary key of each relation, and then to see if there's any foreign key reference to that primary key. So we start with first one. So we have county name. You just look if there's any county name in the schema. So I think then the loss info, this table has county name. So that county name should be the foreign key reference to the primary key of the text. So once again, foreign key always reference to a key. That key can be the primary key or can be the secondary key, but they all have to be key, okay? So if you put the arrow in the reverse direction, then that's or opposite direction, that semantics is totally wrong. So if you put the like this one, okay, the arrows point to the county name of the loss info, then it breaks the requirement for the foreign key, because foreign key always needs to reference to the primary key. And apparently the county name of loss info is not, I mean, I have to take foreign key always reference to a key, okay, not necessarily the primary key. And county name is not a key, okay. It's not a primary key, but it's not a key of the loss info. So that's why that tells that if you draw the direct arc in this direction, then that is wrong, okay. So the only right version will be this notation. So county name of the loss info points to the county name of the text. Okay, so then I think it's done for text. Then we go to the second one, price. So price primary key, I think it has only one key. It's error. So we just see if there's any error in this kind of in one of those relation schema. So I want to emphasize that sometimes even two attributes mean the same thing, but they may use different name. And for this example, since when we did the normalization process, we didn't rename the attributes. So we just simply copied the attributes from the original relation and then split them into different schemas. So that's why I think the trick here, we can looking for the attributes of the same name. But in practice, I think it might not be always true. Then you need to looking for the attributes with the same semantics. So I mean the attributes of the foreign key and the reference key must have the same semantics, same meaning. They do not need to have the same name, but they have to have the same semantics. And another requirement is that if the referenced key is composite, then the foreign key reference to that key must be composite too. And also foreign key must have the same number of attributes as the composite key it referenced to. Okay, so in this sample, I think we have a single primary key and single attribute primary key. So we have this error points to this error. Okay, so that's another foreign key. Okay, so it means that loss info, the error is a foreign key reference to the primary key of the price. But once again, foreign key can reference to a primary key and also can reference to a secondary key. Okay, so both primary key and the secondary keys, they are called candidate keys, but only one of them is picked as the primary key. Then the remaining will be the secondary key. Okay, questions? Okay, if you do not have questions, so I intend to delete this one because this one follow the 2NF normalization, the 3NF normalization. I think that's too a lot of time we do not need to that. We do not need to perform 2 rounds of normalization. We should actually, as long as a relation schema is not in 3NF, we don't care if that relation schema is in 1F or 2F, but as long as it's not in 3F, we always follow this one-step normalization process. So it means that we pick out all partial and transitive functional dependencies because those are not indicate the design is not good. Then we create a relation schema for each one of them. That's in the step 1. So in the step 2, we simply create another relation schema that contains the primary key of the original schema plus any attributes that fully dependent on that primary key. So that's it. So that's why I think you can skip this one, because this one is really confusing. Okay, now for the normalization, so we need to be aware that if we strictly follow the normalization process, then the resulting tables, after we finish the process, we get a set of tables. Each individual table is guaranteed to be in 3NF. So that's very nice thing about normalization process. Okay. And in practice, so far we only study 3NF. So in practice, we also have 4NF, even 5NF. But those high order of the normal forms, most of the time, they're pretty hard to interpret. So that's why we only make sure that as long as our relation schema is in 3NF, we are good. Okay, we do not need to further normalize them into the higher normal forms, because that's pretty hard to understand. Okay. And another one is that I think when we do the physical database design, we may end up going the denormalization. So recall that normalization process usually to split a very big table into a set of smaller ones, okay? And the denormalization process is kind of reverse process, means that we have a set of small base tables. We may want to join them to build a big table, okay? So, but denormalization, although it's one of the practice in the real world, it's kind of strongly discouraged until you really have strong need. So what is the strong need? That means that you have seen a lot of kind of queries that need to join multiple tables together to produce the result. Okay, and if you have a more like a time constraint, so you want to have a real-time application. By real-time means that a query submit to the database, then the result will be returned right away. So if you require a real-time application, and usually the database join operation means that when we combine information from multiple tables together, that process is very time consuming. So it takes kind of longer time. So if that is the case, I think then you probably consider to join several small tables together into a big table, so that the big table can be used to serve the user's the query. Okay. But I think we're going to study cover some kind of physical database design. So we're going to touch the denormalization concept. So in the simplest term, we can use the database views to implement the denormalization. Means that we can create a view that store the results of table joins. So that's basically, and the view can serve, quickly respond to the user's queries. Okay, and also view in a database system, views has very nice property. It will automatically synchronized with base table. So for example, if the view is the join result of table A and B, okay, then the view store the join result. Then if table A and B change over time, then the view will be automatically updated. So that's this kind of automatically updated or synchronization is actually implemented by the database system. So we do not need to worry about the synchronization. So we're going to leave this denormalization when we study the physical database design. Okay. Then this last slide is where also I want to discuss it. So far we study 1NF, 2NF, and 3NF. So we know that if we need to design a database, we have to make sure that every single table or relation must be in 3NF, okay? So in practice, okay, so we don't care if it is 2NF or 1F. We only need the 3NF. Then we may have this kind of a general normal form definition. So this definition basically says that what make a 3NF relation schema. So given a relation schema and a set of dependencies, functional dependencies, then as long as each functional dependencies satisfy this definition, then the relation schema is in third normal form. If it is not, then we're going to undertake the normalization process. So let's see the definition here. So a relation schema R is in third normal form if whenever a functional dependency X determines A holds in R. So both X and A are the subset attributes of the relation R, okay? Either X is a super key, okay? So X, or A is a prime attribute, okay? So as long as one of these two conditions is satisfied, then that functional dependency is okay. So pretty much we will examine every functional dependency with these two conditions. So as long as one of these conditions satisfied, then the functional dependency is good. Okay. The functional dependency is not good if both conditions are not satisfied. That means that X is not a super key and A is not prime attributes. That means A is non-prime attributes. Okay, so if both conditions are violated, then that functional dependency means not good. Okay, so means it, I think most likely if it violates, if X is not super key, that's basically, and A is also a non-prime attribute. So that means that the functional dependency can be either a partial or transitive, okay? So this is called the general normal form definition for the 3NF, because this is very practical, because in the real world, we just evaluate whether a relation schema is in third normal form. If no, we do the normalization. So this, we don't care if the functional dependency is partial or transitive, as long as there is a one, then we need to do the normalization process. So this kind of condition help us to filter out all the partial or transitive functional dependency based on this definition. Okay, so as long as there's a one functional dependency does not satisfy either one of them, means that violate both conditions, then we need to do the normalization process, okay? Then if you're interested, there is a voice cut normal form, also called BCNF. So I think voice cut originally tried to relax the third normal form. And it basically means that as long as X is a super key, that'll be fine, sorry, okay? So it's kind of remove the condition B. So it only means that whenever there is a functional dependency in the relation schema, X has to be a super key. If X has to be super key, then that is a BCNF. So unfortunately, because if you think about the conditions in this definition, a functional dependency must violate both in order to be a bad one, okay? So in order to kind of prevent the relation schema being the third normal form. So must have violated both. But the BCNF actually just means that as long as violate one, then it will be the BCNF. So that's why BCNF this normal form is even much stricter than the 3NF. So that's why BCNF is also called 4NF, means that condition is much stricter than the 3NF. So that's kind of, if you're interested in, you can read more. I think we do have some discussion about the BCNF. Then regarding to the normalization process, means that when we split big schema into a set of smaller ones, It's called decomposition. Then usually we want to keep the two properties. So first one, non-additive or lossless of the corresponding join, means that once we split, like this one, once we split the original loss table, this big one, into the three smaller ones, so that this normalization process is not for nothing. That means that we will not have loss table anymore in the database. Instead, we are going to use these three smaller tables to replace the original big one, okay, the big loss table. So then if we join these three tables together, then we can fully recover this loss table. So the join result will produce an identical copy of this loss table with no less or no more tuples in it. So that's the important thing. It's called no lossless join or non-additive join. So that means that you have to guarantee that after the normalization process, the resulting tables, if we join them, we can simply reproduce an identical copy of the original big table. That is not satisfied in string F. Okay, so that's the requirements. Come on. So it's called non-additive or lossless join. And also sometimes we also want to try to preserve the functional dependency. So I think the functional dependency really describes the relationship among two sets of attributes. So some functional dependencies are actually derived from the semantics and the relationship of the two attributes. Some functional dependencies are actually describing the business rules in a company. So that's why preserving functional dependency is very important. But unfortunately, for some time, okay, when we do the normalization process, we may not be always able to preserve the functional dependencies. So that's fine. Why? Because if the functional dependency, the attributes that in the functional dependency spread out in two tables, then that's not considered a functional dependency. So a functional dependency usually describes the relationship among attributes of the same same relation schema. In other words, the determinant and dependent, those two sets of attributes should be from the same relation schema. So that makes functional dependency more kind of how do I say, much easier to understand. So, but anyway, when we do the normalization, we try to preserve these two properties. If for some reason we cannot, then we always have to make sure that the first property is always true. So non-additive or lossless join. Then we may have to relax the preservation of the functional dependency. So that's the one I want you to understand. So I think regarding in this kind of talking about the relationship, I think it's probably it's good to review. So every 2NF relation is in 1F because that's a requirement. A relation is in 2NF if it is in the 1F first, and then no partial functional dependency. So that's a requirement. Then every 3NF relation must be in the 2NF because according to the 3NF definition, a relation schema is in 3NF, means that it must be in the 2NF, means that no partial functional dependency. Then with actual condition that no transitive functional dependency. So this kind of are fixed relationship. So 3NF does not allow partial or transitive functional dependency. So both are not good, cannot appear in the 3NF schema. For the 2NF, I'm sorry, I think it's showing my network is not stable. Okay, then for the 2NF, it only does not allow partial. So 2NF is not stricter than the 3NF. Then the BCNF, every BCNF relation must be in the 3NF. Okay, so that's we can tell that 2NF, BCNF is stricter than 3NF. 3NF is stricter than 2NF, and so on. Okay, so I think what else? So those kind of, I think this give you a two good example, shows that the relation is in 3NF but not in the BCNF. Okay, so we can, if you're interested in, I think yes, you can read those two slides, but you're not required to understand them fully. So, but anyway, in essence, if you design a database, as long as each relation schema is in 3NF, then you are in good shape. Okay, so that's the most important thing you need to understand. Okay, so any questions so far? Okay, so if you do not have any questions, then I think I post link on the Blackboard and the lessons plan about the normalization exercise. So we're going to review them kind of using some exercise as examples. So let me bring my so you can download them from the Blackboard. So under in the lessons plan, there is a link right above the assignments. There's a link called exercise. Okay, if you you can download this exercise. So I think I hope we can have time to review all three, but we try our best. So I just use these three exercises to show you how to evaluate which normal form the relation schema is in. If a relation schema is not in 3NF, we have to normalize it. Okay, so but usually I think you have to, when we evaluate the normal form, we have to have the information about the keys of the schema. Then we should have the set of functional dependencies. Okay, but here I really want to emphasize that if you don't have any functional dependencies defined on the relation schema, then most likely that relation schema should be in 3NF. Okay. And but you have to make sure there's no functional dependency. So if you do have a set of functional dependencies defined on the relation schema, then you have to utilize those functional dependency along with the information about keys to evaluate if that relation schema is in third normal form or not. Okay, so let's see the example here. So now we have item. I think this data table may be most likely built for a kind of bidding website. Okay, so it stores the item ID, the item that will be bidded by the customers. The last name, owner ID. I think this about owner information. Description of the item, list price of the item. Then the bidder ID. So that's, I mean, we may have multiple bidders, so we need to record the bidder ID. And also the price for each bidder, and then the country that bidders from. Okay, so this table. Okay, so we have a composite key, primary key, item ID, and bidder ID. I think that's maybe the only key here, so we don't have any other information about the other keys. Okay, so we assume each attribute is atomic. Then there are three functional dependencies describe the relationship of the attributes of the item. Okay, so we have item ID determines last name, owner ID, description, and list price. And item ID, bidder ID determines bid price, and the bidder ID determines bid country. Okay, so which normal form is item in? Okay, since we assume each attribute is atomic, then we can safely say that this normal form is in the, is at least in the first normal form. Then once it is in the first normal form, then we can see if it is also in second normal form, okay? So second normal form does not allow any partial functional dependency. In other words, second normal form does not allow any non-prime attribute that dependent only on the partial key, not the whole key. So I think it would be nice if we can categorize these three functional dependencies to see whether they are full, partial, or transitive. Okay, let's start with the first one. Item ID determines L name, owner ID, description, and list price. So what do you think? So is this a partial, it is a full, or it is transitive? So what do you think? So what is partial? So partial means that non-prime attribute have to is dependent only on the partial key, not the whole key. Okay, so maybe we first have to identify what the prime attributes and non-prime attribute. Then we can see. Okay, so we have prime attribute. We need to list all the prime attributes and non-prime attributes. Okay, so the prime attributes basically are attributes that appear in at least one key. So here we assume we only have one simple. I don't know if I'm able to make it. Yeah, we only have a composite primary key. So I think the attributes that make up this composite primary key should be the prime attributes. So it should be the item ID and bidder ID. And that's it. So that means we only have two prime attributes. Then the remaining attributes should be the non-prime attributes because those attributes has no relationship to the primary key. Okay, so that's not means they do not appear in the key. So we have last name, owner's last name, owner ID, description, list price, and bid price and bid country. Okay, so now we have identified both prime attributes and non-prime attributes. Okay, now with this information, then we go back to the functional dependency to see whether a non-prime attribute is dependent on the partial key or full key. Okay, so let's go to the first one. So first one, L name, owner ID, description, and the list price, they all non-prime attributes. So that this means that this functional dependency means that these four non-prime attributes are dependent on the item ID. Okay, then we examine the item ID. So is item ID a whole key or a partial key? A partial key means that if it's just part of a key, not the whole key. So we know the item ID, bidder ID together is a key. Okay, so none of them is a key, but the two work together can be serving as a key. So that's why item ID is considered as a partial key. Okay, so we have this set of non-prime attributes only dependent on the partial key, not the whole key. This is called partial functional dependency. Okay, so this partial because the dependent only depends on a part of the key, not the whole key. As item ID, is a part of the primary key. Okay, so that's the reason it is partial. And we need to Okay. So let's look at the second one, FD2. So FD2 is showing that bid price is dependent on item ID and bidder ID together. Okay, so bid price is a non-prime attribute. So that's indicate bid price is dependent on these two attributes together. And these two attributes actually is the key, the primary key of the item. So this one, in this case, this one will be the full, okay? As bid price is dependent on the whole primary key, okay? So FD1 is a partial functional dependency, and FD2 is a full functional dependency because bid price as a non-prime attribute is dependent on the whole key, okay? Then the last one, the bidder ID and the bid country. So both attributes are non-prime attributes. So the dependent is a non-prime attribute, and the determinant is also a non-prime attribute. So according to this pattern, is transitive functional dependency as both dependent and determinant are non-prime. Okay, so I may want to make it a little bit smaller. Okay, so here I show you how to identify the type of a functional dependency. Okay, so given these three, we have one. I'm sorry, I think I'm wrong. It's not transitive. It's partial. Sorry, because unfortunately I have kind of I start to have migraine yesterday, so my brain is not that clear this morning. So partial. Primary key, okay? So this PK stands for primary key. So in this case, in this relation schema, we have three functional dependencies. Only one is full. So full functional dependency is good. So we don't have any issues with full functional dependency, but we should not see the partial or transitive functional dependency in our design. So that means we have two partial. So then which normal form is this in? So item is only in 1NF. Sorry. It is not in 2NF because of partial FDs. So 2NF does not allow partial functional dependency. So if it is not in 2NF, we even don't need to think about 3NF because 3NF must be 2NF first, okay? Then the question here that if it is not in 3NF, normalize it, okay? So the normalization should be simple. So we simply just follow that algorithm, normalization algorithm, okay? So recall that normalization algorithm always contains two steps. Step one, I think my display response is so slow. Okay, so basically, it always contains two steps. Okay, the first step we're going to create a relation schema for each partial for each partial and transitive functional dependency. So then we go back to this one to identify what are the partial. So we have two partial, okay? So the FD1 is 1, okay? So to basically when we create a relation schema, we solely based on this partial. So for the FD1, the partial, we need to create a relation schema, just solely use the attributes in the partial. So maybe I do the item info. Okay, so then we simply list all attributes on both left hand side and right hand side. So item ID, owner's last name, owner ID, description, so that's basically what we have here. Okay, then once we list all attributes in FD1, then the determinant of this really functional dependency, will be the primary key of this new relation. Okay, so pretty much we create a functional dependency based on the first partial. We create a relation schema based on the first partial functional dependency. The second one, we're going to use FD3 because that's also partial. Then we create another relation schema. Okay, so the reason I copied the partial functional dependency, so I want to show you that each relation schema is derived from. So the second one will be derived from the FD3, which is also partial. So maybe I got the bidder info, okay? Then it only has two attributes, bidder ID and a bid country. Then the bidder ID will be the primary key of this new relation. Okay, now we are done with step 1 because we create the relation schema for every single partial functional dependency. Since we don't have the transitive, so we do not need to create one. Then for the second step, and if we do have a full functional dependency, because full functional dependency really specify which non-prime attributes are dependent on the whole key. So in this case, we have item ID, bidder ID, the bid price. So we can simply create a schema based on the full. Okay, so sometimes we may not have the full functional dependency specified in the question. If that is the case, then you're going to use kind of strike. So you strike out whatever attributes that appears in the partial appeared on the dependent side of the partial functional dependency. Then the remaining will be the one that you should include in the schema created in step 2. So here we have the full functional dependency. So we just need to create, I think, the full functional dependency. Basically, I think I call it bid info, okay? Because talking about, so it has item ID, it has bidder ID, it has bid price. Okay, so still I think during the normalization process, you have freedom to give the name to any new relation schema, and also you feel free to change the attribute's name if you want. Okay, So now we have 3. Okay. So let's go back to the original things. So assume that if we do not have this functional dependency, okay, if we do not have this functional dependency, then what we're going to do? So then we just based on these 2 partial functional dependency, because we're going to create one schema for each one of them. So then we know that we only identify the attributes on the right side. So that's the dependent attributes. Then we simply just cross out them. So we have L name, we cross out this one. We have owner ID, we cross out this one. We have description, we cross out description. We have the list price, we cross out list price. So that's coming from FD1, okay? For the FD2, the same thing, we only cross out the attributes on the right side, or the dependent attributes. So now we have bid country. Now the remaining attributes should be the one that we need to include in the final relation schema that produced at step 2. Okay, so that's in this example, I show you that if in the case the full functional dependency is not given in the question, then you just simply cross out the attributes that appears on the left hand side, okay, of your on the right hand side of your partial functional dependency. Okay, questions? I think also it is also true that if you have a transitive functional dependency, you also need to cross out those attributes on the right side, so the dependent attributes in the transitive. Okay, so let me recover them. Oh, sorry, I didn't do all of them. Okay, now finally we have with 3. Okay, so we have item ID, bidder ID. So I may need to make them smaller. So then final results. So normalization is you do the normalization for purpose, means that you're going to list all relation schema you generated, okay? And this relation schema will be used to replace the original one. So this tray will be used to replace the item scheme. So means that in your practice, if you need to implement this database, you no longer need the item table. Instead, you're going to have 3 smaller tables. So item info and bidder info, and then bidding, maybe I put into the bidding info. Okay. Okay. So I think that's maybe too small. I mean, you'll probably be able to see that clearly. No, I think it's okay. Okay, now we're not done yet. We still need one last step to identify the foreign key and the reference key. So same thing, we can scan in each relation to see if there's any foreign key reference to the primary key of the relation, or if the relation has also multiple keys, we just need to make sure that if there's any foreign key reference to one of those keys. So in this example, I think for each relation, we only have one key, and that key is underlined also as primary key. So then we can tell that bidding info has item ID, and this item ID should be the foreign key reference to the item info's item ID. So once again, for the bidding info, this relation, we have both attributes underlined. So that's indicate those 2 attributes together is the primary key. So item ID alone is not a key, okay? But the item ID in the item info is a key. So that's why item ID in the bidding info table is a foreign key reference to item ID of the item info. I think second one will be the bidder ID of the bidder info table is a foreign key reference to the bidder ID of the bidder info. So now I think at this moment we are done with the normalization process. So in the real world database, you may have multiple tables, okay? So if some tables are not in 3NF, then you need to normalize it, okay? So then after you normalize every single table that not in 3NF, then you're going to finalize your database schemas, okay? So that's the important thing you need. Okay, good. Any questions? So I think we still have time. Let's start the second one. I think second one, yeah. Second one, I may want to leave it for you to. Why not you working on the second and third? Okay, so then I can discuss partial one. So then you work on the second and third one. In next class we can discuss solution, because this normalization process for sure will be in your term exam, since you only have one term exam. So I really want you to understand it very well. So this is a similar question. So we have a schema given. So in this schema we have student ID. I think this capital S stands for student name, student phone number, student department ID, and student department name. Then we have advisor name, advisor phone number, advisor department, and advisors and a term. Okay, then there are 4 functional dependencies given. So we have SID determines S name, S phone, S DPT ID, S DPT. Okay, then we have advisor name determines advisor phone and DPT. Then we have SID term determines advisor name, and SDPT ID determines SDPT. So the first one, I hope you still remember this kind of a notation. So the superscript plus or super plus indicate this. We are trying to calculate the closure of SID. Okay. So to calculate closure of SID, we just simply follow that algorithm. I think in the class we discussed. Sorry. Let me see. I want to. So this. I don't want this to be the superscript. Okay. So when we do the SID closure, we first initialize that closure with SID itself. Okay. And then we're going to apply any functional dependencies that at least the determinant start with SID. So SID as determinant. So given this 4, so the first one, FD1, has SID as determinant. FD3 is not, because FD3 means we need both SID and a term in order to derive the advisor's name. So in this case, means that we can only apply to, sorry. So okay. So we apply to the SID determines S name, S phone, and SDPT ID and SDPT. So based on this functional dependency, we know that SID will determine all the other dependent attributes name. So we're going to list all those dependents of the FD1. So we have S name, S phone, SDPT ID, and SDPT. Okay, so this we got this one by using FD1. Okay, so now we will see if there's any functional dependencies that does contain, I think, yeah, it's fine. So probably let me delete this one to be easier. So we don't have this as DPT, okay? I think FD1 should be revised. Okay, now we see if there's any functional dependency whose determinant is included in this set. So SD1, we use FD1 already, so we do not need that one anymore. So for the FD2, it does require the advisor name, so we don't have advisor name here. So we move on to the FD3. FD3 has SID and term. We do have SID but not term, so as FD3 will no longer be used, will not be able to apply it, no longer be used. Then FD4, we do have SDPT determines SDPT. So we do have the SDPT ID in the closure. So that's why we could further update the closure by adding. So we simply copy all attributes in the original closure and then add the new attributes that's the dependent of FD4 in the set. Okay. Now I think that's it, because if we evaluate, so we have already applied FD1 and FD4, so they no longer be used. So we only focus on FD2 and FD3 to see if the current closure does have the determinant of FD2 and the determinant of FD3. So I think the answer is no. So now we end. So it means that SID closure will be the SID, S name, S phone, SDPT ID, and SDPT. Okay. So that's it. So that's for the closure. Okay. Now I want you to maybe at home working on these two questions independently. So the normalization 2 and then also normalization 3. So for the normalization 2, in order to identify the normal form of student, we first have to specify the prime attributes and the non-prime attributes. Then we're going to utilize the information of prime attributes, non-prime attributes, and the primary key to evaluate what type of the functional dependency each one is. So there's only 3 types: full, partial, and transitive. So we need to label each one of them here. So once we label them, then we're going to determine whether this student relation schema is in second normal form or third normal form. Okay. Okay, so that's what you need to do. So any questions? So I strongly encourage you to finish the all of them, and then we're going to discuss in the next Tuesday, and then I think your homework is due on next Tuesday by midnight. So if you're not very confident, sure about the quotient normalization part, then you can wait till the Tuesday when you finish class, then you can work on the problem. Okay? Any questions?
No, Dr. Wu.
Okay, good. So if you do not have any questions, then we are done for today. Thank you.
Thank you.